Hello and welcome to this video on correlation and regression in R. In the previous video, we had already seen how to set up a correlation regression model in R. In today's video, we will see some more functions related to correlation and regression. The data set that we take in this video is named Swiss. It is an inbuilt data set in R, and we are saving it as a data frame in a variable named regdata. As I execute this command, you can see that we have a data frame with 47 observations and 6 variables. The variables that we have in this database are fertility, agriculture, examination, education, Catholic, and infant mortality. The description is given right in front of us. Fertility is the standard fertility measure that we have. Agriculture is the percentage of males involved in the agriculture as occupation. Examination is where percentage draftee is receiving highest marks on army examination. Education, percentage education beyond primary school. Catholic, whether the percentage of Catholic people. And infant mortality is live births who live less than 1 year. So if I show you the data over here, this is how the data looks like here. So what we will use this data for is for estimating the dependence of fertility or establishing the relationship of fertility with these explanatory variables. So we have 5 explanatory variables, namely agriculture, examination, education, Catholic, and infant mortality, which we will use to estimate the fertility. Clear? Let us first look at the structure of the data. When we look at the structure of the data, we see that fertility, agriculture, and infant mortality and Catholic are saved as number type, whereas examination and education are all integer type. Clear? The first thing that we look at is to prepare a correlation matrix in R. A correlation matrix, as we know, gives us the relationship between variables, and it is of interest to us when we want to find out if there is a relationship that is built between 2 or 3 explanatory variables, because that can cause a problem of multi-collinearity. If there is a very high correlation between 2 variables that are explaining a dependent variable, then that is a cause of a problem in a linear regression model. Clear? As we know that one of the key assumptions is that the explanatory variables need to be independent of one another. So any sort of correlation, whether positive or negative, is going to be bad for the model. First things first, what we do is we create a new object called data1 and we save it as a matrix. You can see clearly here that we have taken the dataset reg data, but we have eliminated the first column, which was the fertility column. So what we are basically doing is that we are creating a matrix of all the explanatory variables. Clear? As I execute this, we get data1, and now we prepare the correlation matrix with the help of a function called cor. Clear? Cor function helps us to prepare the correlation matrix, in which we have to just pass the name of the matrix, that is data1, and we save it in the cormat variable. I name it as cormat. I execute this, and when I execute cormat, I can see the matrix right in front of me. As expected, the diagonals will obviously be 1 because it will have 100% relationship with itself. So agriculture with agriculture, examination with examination, education with education, and so on and so forth. Then when we see the upper triangle and the lower triangle of the matrix will obviously be equal to one another, because if you see the agriculture and examinations correlation, it should be the same as examination and agriculture over here. We can see 3 figures over here. One is agriculture with examination, and the other is agriculture with education, and the third one is education with examination. These 3 seem to have pretty strong relationship with one another, where we can see education and examination have a negative relationship with agriculture. On the other hand, education and examination have a positive correlation with one another. So these key insights help us to analyze when we create the linear regression model, that the results that we are getting are correct, not correct, which variables to be kept, which variables to be dropped. So that is why it is important for us to understand the relationship between the explanatory variables. Next up, what we'll try to do is we'll try to visualize this matrix through a graph. So the function for that is known as the cor plot. Cor plot does nothing but gives you a visual aid to see the correlation matrix that you have prepared. So if I write cor plot and pass the correlation matrix through it, you can see that we get this beautiful graph for ourselves, where blue color denotes a positive correlation, The peach color denotes a negative correlation. The deeper the color, the darker the color, the stronger the correlation. The lighter the color, the weaker the correlation. Clear? So you can see that the ones are complete dark blue. These ones, if you remember, education and examination with agriculture were around minus 60, minus 0.68, minus 0.69. So they were pretty high and negative. This one on the other hand, education and examination was positive 0.69. Clear? So that is why it is blue in color. As you can see here, there can be different ways of showing this graph. Here we are using circles as the object. You can use squares. Here I am using pie chart. You can see here when I make the method equal to pi, by default it is circles, but when you change it, you can have something like this. In pi, what you see is again blue is for positive, peach is for negative. When there will be a positive correlation, it will start working clockwise. So this one, if you remember, was 0.68 or 0.69. So this becomes 0.75, this becomes 1. On the other hand, when it is negative, it becomes anti-clockwise. So this was also around 0.67, 0.68. That is why it shows pretty high correlation between these variables. Clear? So the correlation matrix can either be found through the core function, or it can then be plotted also through the core plot function. Okay. Next up, let us try and predict using our model if we have some new data that is being fed into us. Clear? So we prepare a model named model 1 where we are taking fertility as the dependent variable and all the other variables as the explanatory variables. Clear? Data is reg data. I execute this command, and when we see the summary of model 1, you can see this was the model. As I said earlier, this was the model. You can see the residuals. This we have already seen in the previous video also. You have estimates of each and every variable for yourself, standard error, t-value, the probability that gives you the z value, the p-value. So you can see which ones are significant, which ones are not significant. You can see clearly that examination is not significant. Examination is not significant at all. One of the plausible reasons can be that examination had a very high correlation with education and agriculture both. So that can be a case that education and agriculture had already taken into consideration a large effect of examination on fertility. Clear? But we are getting single point estimates of all our variables. What if we want a confidence interval? You can also find out the coefficients like this. See, intercept is 66.91, agriculture is minus 0.17, examination is minus 0.258, and so on and so forth. What if we want a confidence interval for the estimates as well? So for that we have a function called confint, and in this, if we pass the model, we can see that for every single explanatory variable coefficient we have a confidence interval that is given to us, a confidence interval for the estimates of the variables. Clear? By default it gives you a 95% confidence level, confidence interval. If you want a 90% confidence interval, then obviously you can use a second argument named as level and put it equal to 0.90. Clear? As we had seen earlier, that examination was one variable which we felt was not significant enough. So in model 2, what I have done over here is I have dropped that variable. And I've also dropped the agriculture variable. I've dropped both the variables. If I take you up again, see, agriculture is also not very significant. Clear? And examination is not at all significant. So I've dropped both these variables in model 2, and now I'll run the model 2 and execute it. Now if I compare summary of model 1 and model 2, one of the key ways of comparison in multiple regression, correlation regression, is the adjusted R square. The R square will obviously not give you the true picture. Adjusted R square will give you a true picture. So adjusted R square was 0.671 earlier in model 1. In model 2 it drops to 0.639. So definitely adding both those variables or removing both those variables did not actually bode well for us. But that is not the key thing that we want to focus over here. As I mentioned, that the key thing that we want to focus over here is if we can actually predict the explanatory variable, we can actually predict using the explanatory variables new inputs how the dependent variable would be. So for example, if I give you a number for education, a number for Catholic, and a number for infant mortality, can you predict using your linear regression model what would be the fertility rate? Clear? So the new data that we have been given is that education is 20, Catholic is 50, and infant mortality is 10. I create a new data frame. I create a new data frame as new data. Clear? Please make sure that the headers over here are exactly the same as the ones mentioned over here. Clear? So education is 20, Catholic is 50, and infant mortality is 10. I create a new data frame for this. This is the new data that has been given to us, and based on this data we will predict the level of fertility. Clear? Based on this data we will predict the level of fertility. So I use the predict function. The first argument is the name of the model, and the second argument is the data that we want to use to predict the dependent variable. Clear? So predict, we are using model 2 and the new data frame. When I execute this, you can see that we get the fertility prediction to be 51.25694. 51.25694 is the level of fertility that is being predicted using model 2 when we have been given the new data for education, Catholic, and infant mortality to be 20, 50, and 10 respectively. What if we wanted a 95% confidence interval for the prediction as well? Then I would have inserted another argument called level and write it as 0.95. Here. Now what is the difference between this one and this one? Let us try and understand this. First one, if you see, I have written predict model 1 to new data. Till the second argument, both of them have the same arguments. It's the third argument when I have actually changed, where I've written interval is equal to confidence over here and interval is equal to predict over here. So what do these third arguments depict for both the models? Let me just run the first one first. This is the first one. I'm getting 51.25694 as the prediction, and for this one also I'm getting 51.25694. But if you see, the confidence interval is different for both. So if you read this, I've clearly written it out here, that when interval is put as confidence, it means we are predicting for the mean response. Using the linear model. However, when we are putting interval as predict, that means we are predicting for that individual response for the linear model. Clear? So if we want to predict the mean response, then we have to put interval as confidence, and when we have to predict for the individual response, then we have to write interval equal to predict. By default, please be careful, by default it will give you the interval as confidence, that is, it will give you the mean. Clear? It will give you the mean response. So this is the way you predict data using the linear regression model. There are two methods. One is where you can use the confidence interval equal to confidence, which means for predicting the mean response, and the other is interval equal to predict, which helps us predict the individual response. The level can definitely be changed depending upon the desirability of the analyst. Clear? So this was it in this video. We looked at a correlation matrix using the core function. We use the core plot function to plot that matrix into a graph. Then we looked at confint to find out confidence interval of the estimates of the explanatory variable, that the beta coefficient that is. And lastly, we use the predict function both for individual and mean response to get prediction of the dependent variable using the explanatory variables. Clear? Thank you very much.